Good morning, everyone. Thank you for joining us today on the first BINDT Lubrication webinar of 2026. My name's Jade Thompson and I will be your host for today. I work for SKF as the Recon Oil and Lubrication Programme Manager in the UK, and the British Institute of Non-Destructive Testing has several committees which aim to develop and promote the practice of diagnostic engineering and testing. Today, our Lubrication Working Committee will be covering the topic of when lubrication causes problems. This is a subject which will take much more of a forefront in maintenance around the UK over the next few months due to the worrying oil supply issues impending. With that in mind, we would like to ask our audience today a question. Please provide your responses in the chat function, and the question is, what are your biggest concerns around lubrication right now? The BINDT committee members today are on hand to help with advice on how to cope with potential supply chain disruptions in a sustainable and reliable way. As we work through the webinar today, please drop any questions for the presenters in the chat and we will pick them up in the panel or after the webinar. We will have 2 presentations and then a short break and then the last 2 presentations for today. Our first speaker today, Adam Cutler, is the chair of our Lubrication Working Committee and he's been surrounded by lubrication analysis since birth. He's the founder of Oil Analysis Laboratories in the UK. He also operates learnoilanalysis.com, which is a platform that provides free online training. Adam will also be presenting in person at the BINDT CM conference from the 9th to the 11th of June in York this year. Adam will provide us today an insight on what harm the wrong oil can do in application. This is a problem we see very frequently. Thank you for joining us, Adam. Are you okay to share your presentation and then I can hand over?
Okay, thank you very much, Jade, and thank you for the introduction there. So today I'm going to talk about what harm can the wrong oil do. So first of all, why the topic? So if we think about oil suppliers or lube suppliers globally, you may recognize names such as Shell, ExxonMobil, BP Castrol, Total, Valvoline, Fuchs, Chevron. All these brands you recognize throughout the industry, and they all have their own market share. And this is some estimates of market share based on the litres of oils they sell each year. But this is based on litres of oils, but this may not be the best way to measure it. And so in terms of actual customer perception, this information is wrong. So the most popular oil in the world sold right now is actually unknown. So most of all the oils, in fact, more than all the others combined, people do not know what actual oil they're using. So many people don't know what oil is in their car or the machinery. And so if we expand that a little more on here, we have what are the most common brands people use. Unknown is number 1. Then there's I think it's, so that could be I think it's Shell, I think it's Castrol, I think it's synthetic, or it could be a mix of. So it's a mix of one, I topped it up with another. And so not knowing the right oil is actually a real problem in the industry. So does the type of lubricant actually matter? So that question, the answer there is actually not right. It's wrong because we need to understand how lubricants work and why, and that will help us understand things. So let's talk a little bit about the function of a lubricant. So the most obvious one people think of is it reduces friction. So separating the surfaces and allowing things to the components to move past each other. We also think of it as preventing wear. Obviously, you don't want things to wear. It can also dissipate heat. We also want it to prevent corrosion. So if we get water into the system, we want it to remove it and prevent it from causing corrosion to components. It can also clean. Now, this can be through additives, so detergents, but also physically just transporting the oil to a filter that does the cleanup job. As well, an overlooked feature is the ability to seal. So if you take an engine, for instance, the piston rings are often thought as sealing, but it's actually that little small tiny layer of oil beyond the piston rings between that and the sunderliner that does the final seal to prevent leakage of combustion gases. And then anyone who's in the hydraulic industry, there will be the ability to transmit power and dampen shock as well. So let's start off with the first one, so reducing friction, which is the one that most people think of when you think about what's the function of a lubricant. So what affects friction? Well, there's a few factors, but one of the key ones is the viscosity. So viscosity is resistance to flow, but in layman's terms, it's how thick an oil is. So we can see here, we've got on the left-hand side, we've got a very thin oil, and on the right-hand side, a very thick oil. Obviously, it has more resistance pouring from one container to the other, so pours more slowly into one container than the other when it's a thicker oil. So how do we measure viscosity? So there's several ways of measuring viscosity, but a common way of doing it is kinematic viscosity, which you have a oil-filled bath that we, under gravity, drop the oil down one end of a viscometer tube, and it then reaches the final point at the bottom under controlled temperature, and then we know by the time it takes to get from one point to the other how thick the oil is. So if we just take this bath here, so on the left-hand side, I've got three tubes on here I've highlighted. I'll just highlight for you on screen. You can see I've highlighted those there. And if we just put some oil down each of these tubes now, so we're just going to put some down each of the tubes, and we can see that this one on the right-hand side is actually hit the bottom before the first one, although that started first, actually reached it and is now finished. Now, the reason for that is a much thicker oil, has more resistance to flow, and so takes longer despite starting earlier. So what happens when an oil is too thick? So if we think in something like an engine, for instance, obviously if you think you're trying to move components for a very viscous oil, that's going to give a lot of resistance and a lot of drag. That's going to lead to increased pump load, and it's also going to reduce to lower fuel efficiency. Whereas a thinner oil is going to have less drag, and so it's going to be easier to flow, and so it's going to be easier to pump it around, and so you get better fuel economy. And that's why a lot of modern formulation oils tend to be thinner, because it gives less drag and gives you a better fuel economy as a result. But can it be too thin? So this actually brings us into our next area, which is preventing wear. So a too thick an oil, as I highlighted before, if you've got something that's too thick, you have a high energy consumption, but you get a really good film thickness. In contrast, if something is too thin, you get a better fuel economy, at least at the start, but you get more risk of metal-to-metal contact. So you don't want an oil that is too thick or too thin. You want this Goldilocks zone of something just right that is thick enough to give surface separation, but not too thick that's going to lead to increased drag and increased energy consumption. So what happens to the film thickness? So if we think we've just got a brand new component now, and we just take a plain bearing, for instance, as the surfaces move past one another, we think of them as being perfectly smooth, and they look very perfectly smooth to naked eye. But at a microscopic level, they have these surface imperfections, and we call these asperities. And these give little troughs and valleys as the surfaces move past one another. And you can imagine these will bump into each other as we move them. So as we see here, they're moving past each other, and we get these materials break off. And these then deposit and react with lubricant additives and form what's called a shear mix layer or boundary lubrication. And what happens is that under normal circumstances, you have the full fluid thickness, so the oil is separating the components. But under like reasonable load, but not overloading, you can have it where the actual surface actually comes into contact just from the additives itself. But if you take this too far, you can get metal-to-metal contact, which is abnormal wear. So the boundary lubrication is typically normal wear, but if you overwhelm that, you get abnormal wear. So on here, if you have a look, if you get to the abnormal wear from metal-to-metal contact, you lead to sliding wear. And you can see on this particle here, we've got almost like a grain to the material. These are called striations, and these are significant in a sliding wear contact like I just showed. So if we have our normal system here with a full fluid thickness, and if we have one which has got a too thin a film thickness, we can have boundary lubrication touching and then going beyond and actually breaking that and getting to metal contact. And this leads to increased wear in the system. So I've already pointed out that viscosity affects the first two functions of a lubricant. And that's because viscosity is the most important property of a lubricant. So much so, I'm going to talk about it again now. So we talk about dissipating heat. And we talk about viscosity index. So I described earlier when we talked about viscosity that we have a temperature controlled bath. Now that's because that all oils thin with increasing temperature. So if we just take a classic thing, I always think of this when I'm cooking. So if I've got a cold pan here and I put a blob of oil in it, when I heat it, that oil spreads out across the pan. That's because it is reduced in viscosity and so has less resistance to flow. So it flows around the pan much easier. So we measure this change over temperature in something called a viscosity index, and that looks at the temperature at 40 degrees Celsius and 100 degrees Celsius. Now, if we just take this example system here, where we've got an operating temperature of, say, 95 degrees Celsius. Now, this could be an engine, for instance. All the oils give the exact same target at operating temperature, so they're equally as good as far as the film thickness at operating temperature. But if we to take this oil and extrapolate off here, it's going to be very thick at cold temperatures, whereas this one's going to be very stable. This is technically the perfect viscosity index. It's like infinite here, but this is unrealistic. You'll never get this, but you try and get as close to this as possible. So who will this suit? So someone who's working in these cold conditions here, they're trying to start the engine. They want this to be as close to this perfect line here because they want it to not get too thick when they're at colder temperatures. But this doesn't necessarily suit everyone. So if we take an oil that is being used to transfer heat away from a component, you want actually that as soon as it heats up to get very thin very fast so it can flow away to allow fresh cool oil to go and cool down the component. So a very, very low viscosity index would be desirable in those circumstances as opposed to the high viscosity index when you want good temperature stability. So another thing you may be thinking of, isn't the oil being oxidized from the heat here? So this is where we come on to prevention of rust and corrosion and oxidation. So all lubricants contain anti-rust and antioxidant additives, or called an R&O additive package. So all oils contain these in their lubricant formulations. It's part of the basic oil formulation. So you could argue, are all oils suitable for corrosion prevention? Well, it depends. So if we take something like an ester, so there's several types of esters, but some of the key properties some of the esters have, something like a phosphate ester has good fire resistance. Something like a biodegradable ester, obviously by the name, they are biodegradable, so have good environmental credentials, but they're also good solvents, and they tend to have good, very high viscosity indexes as well. So all these could be desirable properties. And they'll all have rust and antioxidant additives in their additive package, but esters are made from acid plus alcohol equals ester plus water. But we can reverse that reaction. So if we add the water, we can split the ester back into an acid, and that acid can cause corrosion. So in this case here, a wet environment is not the ideal circumstances to use an ester-based lubricant. So we can see here, we have a test specimen, and normally we do this test over 4 or 24 hours, depending on the client's requirements. This is after 40 minutes of testing, and this is not the anti-rust corrosion additive being spent. This is actually the oil has been split because we mix oil and water together to see how well it prevents corrosion. But the water had split the oil so it split the ester into acids, and this was causing corrosion. So is it just the base oil and antioxidants that's causing issues? Well, no, it can also be other additives as well. So a common one is EP, extreme pressure oil additive, which is used in many, many gear oils and gives that sulfury, unpleasant smell you can smell in gear oils. Now, these are really good for wear protection, but one of the disadvantages is that EP can attack copper components. And this can eventually, over time, lead to copper sulfide formation and eventual, over a very long period of time, tarnishing and dissolving of components in a gearbox over time. And the way we measure this in the lab is we do a copper corrosion. So we simulate that environment and we take a copper test strip and see how much tarnishes. You can see this specimen here is actually not looking too healthy compared to, on the left-hand side, what a nice, fresh, healthy specimen should look like. So we can also, as well, the function of a lubricant includes cleaning and transporting the debris. So the thing I want you to get from this is that the dirty oil is a wrong oil. So if the oil is dirty, this is not the right oil for you. Now, I'm not going to go too much into this. because following on later on, the last presentation will be Dimitri, so you've got something to look forward there to hear more about contamination effects. So stay tuned for that presentation. Lubricants are also required to seal, as I mentioned before. So a common issue you have is when switching from one brand or one type of oil to another in large lubricated systems, you can lead to shrinkage or swelling of seals, which lead to them not setting right in the housing and leading to small leaks throughout the system. And this is one of the things when you're switching in very large oil systems and large lubrication systems, is to actually check for seal compatibility. So some of the ways you can do this is you can measure an aniline point. So you can measure the inherently the aromaticity of the products, and this will give an indication of how well and how compatible the oils will be. You can also do direct specimen testing. So you can take one of the seals and you can take the old oil and you can take the new oil and see how the swell effects would be on that on that specimen. So we can see here we've got two equally sized specimens here. Now this one you can see is very slightly bigger than this one at the bottom. So you can see this is actually swollen a little bit more. Now, if we wanted it to be like this one, they would have gaps here because we're not getting enough swell. Or if it was vice versa, we wanted to have this one, and this is what the alternative product is, it could overswell and lead to, again, disruption of the seal. We also want to, as well, dampen, shock, and transmit power. So if any of you have ever put your foot on the brakes and it's not gone too well, this can be down to air in the brakes. And so obviously that's a safety issue, but this also happens in anything in hydraulic power. So air obviously is compressible. And so foam in a lubricant or high air release tendency to a lubricant can all lead to uncontrolled movements, can lead to safety issues because it's uncontrolled, but can also over time, because air is compressible, that air gets superheated. And so over time, that heated air will burn the oil around it and form little soot particles. And so you can actually get a process called microdieseling. So the oil actually over time starts to soot. So in conclusion, what I would like to get from this is that oil analysis assesses all these parameters and looks at all of these aspects of have you got the right oil for the right purpose. So it'll look at viscosity, looking have you got the right film thickness. It'll look at the elemental analysis to see are you getting wear and have you got the right additive pack there. It'll look at infrared to see you've got the right type of lubricant. It'll look at viscosity index to look have you got the oil is working over different temperature ranges at the correct amount. It will also measure how spent a lubricant additive is and how much resistance a new lubricant will have to depletion. It'll also look at the corrosion and air handling and water handling properties and all these properties, and all this can be found out from a single oil sample. So I'm not going to answer any questions now. This will be all done at the end in the panel session. But I'd just like to remind everyone that there's no silly questions. It's better to ask before doing and to put these into the webinar chat, and we'll all answer at the end. So I'm just going to hand back to Jade now, and thank you very much for listening.
Thank you, Adam. That opening message that you started with is really key. The most common oil type in use is unknown. My background is oil analysis lab, the same as everyone presenting today, and that resonates with us all massively. And I think it's very important information that's often overlooked by end users. It's for us very difficult to distinguish between some contaminants and additives or failures if we're unsure what we're dealing with in the first place. We often have end users claim that they don't have lubrication issues, so hopefully your presentation today has shown that a lubrication issue doesn't always appear to be a lubrication mechanically on site. Gwyn Simmons' presentation later will also shine a light on the importance of correct information and data. Before we move on, I'd just like to remind everyone we have got the Q&A section open today in this webinar for all your questions on specific presentations, or hopefully to answer our question that I asked at the beginning. What are your biggest concerns around lubrication right now? So our next speaker is Danny Shorten, and he's been in the industry for a lifetime. He's currently heavily involved with John Crane in the development of asset condition maintenance, monitoring, managing for critical rotating equipment. Danny's also been awarded a prize from BINDT for comedy and this is for his contributions to society via condition monitoring, predominantly in the marine sector. Danny's been working with BIN UK standards and the ISO on a soon-to-be-released certification for asset condition management specialists. So if anyone's got any questions on that, Danny is your person to speak to. Today, Danny's going to help us explore the merits of condition-based lubrication. Thank you for joining us, Danny. We can see your presentation and your 20 minutes start now.
Thank you very much, Jade. I appreciate it. And thank you very much to Adam for framing what we all like to see, which is a fully understood oil analysis suite. What I'm going to talk about today is possibly those assets where we don't necessarily do oil analysis, and therefore we don't necessarily have an understanding of the asset condition within the system. Now, in a recent survey, 90% of people, when questioned, agreed that lubrication was critical, but only 30% of those suggested that they are actually achieving acceptable performance. Now, this was recently highlighted on a webinar which Rafe performed recently. For those in the community who get on social media, you'll know Rafe is very knowledgeable and has a broad understanding. And he suggested one of the things we need to do within most companies is identify a champion who owns all the areas of lubrication. Not necessarily that he or she is responsible for performing the activity, but so there's a degree of oversight, someone who can be consulted and who can actually fight for good practice and behaviour, simply because we believe that the gap between the 90% who believe it's critical and the 30% who believe they're achieving a good standard is likely due to prioritisation, because we're very much focused on performance of production, of getting the products out, or maintaining and fixing failures. Now, we have a proliferation of maintenance management activities. We have sensors. We've got the opening dialogue with AI. We use labs. There's the opportunity for on-site mini labs and portable devices to create a matrix of capabilities to allow optimal risk management. Now, my message really is best practice is all well and good, and we need to know what it is, but good enough is good enough. And most companies don't really understand where they are on that particular paradigm or that continuum. They will be used to doing it a particular way, and they will be accepting a certain amount of risk, either knowledgeably or otherwise. So one of the messages today is how can we actually increase our knowledge? Now, my company, John Crane, is involved with the manufacture of high-end mechanical seals, filtration products, couplings and bearing isolators, and we operate in most countries, and in the majority we're in large process and petrochem where we've got large significant asset bases. Now, we realise that many of our products are often changed out earlier than we would have liked because of their design requirement, but very often this is a result of a no-fault situation or an opportunity that's presented itself because a bearing has gone down or we've had misalignment due to external factors. So this is why understanding machine condition is critical to us. Now, on the screen you'll see John Crane Performance Plus window, and the area I'm involved in is asset condition management, and this really frames the discussion we're going to have today over the next 20 minutes. Now, the core problem, I think, is that we spend a lot of time doing stuff we don't necessarily need to do. We do stuff that doesn't impact asset health, and we're changing oils, for instance, when they don't need to be changed, and in doing so we're introducing interventions that introduce avoidable risk. We're also having to stop plant or go onto AB or increase issues around safety because we're getting the tools out of the box and we're actually going on plant to do stuff which may or may not be necessary. So we're consuming maintenance capacity and the consumables, but we're not really aware of whether that's necessary or not. However, doing something often feels better than doing nothing, and I'm going to argue the case that actually doing nothing sometimes is actually better than doing something. Now, when we look at a sort of medium-sized site, the calendar structure would normally look like this. So if you've had an oil survey or you've updated your maintenance management processes recently, you'll be doing oil analysis on probably your critical items. And these will tend to be driven by the sump size, i.e. the ones with the most oil in, or the criticality to operation. And you'll be sampling them on a monthly or quarterly basis. The smaller systems, where you are not really happy to make a commercial decision to take an oil sample, box it off, send it to a laboratory 4 times a year or 12 times a year, these will be on some kind of fixed schedule. Nominally, 3-year oil change and an inspection process for top-ups. Your grease systems will be visited according to a calendar schedule. Somebody will walk a line with a grease gun and they will apply grease according to that schedule. So the truth of the matter is, let's say in this example we've got 250 lubricated sumps, only 10% of those are going to be sampled, so you've only got knowledge of the internal condition of the oil and the machine in 10% of those assets. So 225 are unknown commodities. Now we can inspect from the outside, we can have a look for leaks, we can do all sorts of stuff, but we don't really know what the condition of the oil is, so we're going to change it based on a calendar basis. So 225 oil changes we're going to do whether we need to or not. And that equates to about 75 oil changes annually. So that's more than one a week if you spread it out. And in addition, everything is greased whether it needs to be or not. And that leads to a problem because we can under and over grease systems and we may or may not know what we're doing. So can we do it differently? This is the question I want to ask everybody. Can the oil be changed or a system re-greased only when it's necessary? Well, the answer is of course yes, but there's a commercial consideration as to how we achieve that knowledge. So if we know that the oil is unsuitable for further service, then we'll change it. But if it's okay, we can leave it, but we need that knowledge. If we know it's contaminated beyond repair, so it's something a filtration system can't deal with, then we can change it and we can clean it. But if it's clean, just leave it. If the oil's degraded, same thing. Change it or leave it. But if we can prove that we don't need to do it, then we can leave it. And it's not negligent, it's an active decision. So we're actually changing something from a scheduled activity to a decision window. Now the sort of things that we can do on site, for instance, because the solution is to test on site, is to look for the issues Adam was talking about earlier. Is it the right oil? Is it wet? Is it dirty? Has it aged? And there are on-site tests we can do for that. We're not concerned here about machine condition, we're simply interested in the condition of the oil, i.e. can we leave it there or do we need to change it? So I'm not really interested at this stage in wear metals. If I was, I would send it to a laboratory or I'd build a mini lab on site to do that, but this is not the purpose of the discussion today. Similarly with additive depletion, we're not really looking at that, although there are some devices that can help us. So what tools are available? Now this of course depends on the commercial argument for doing on-site analysis. So we can do simple things with water, such as a crackle test. We can do more involved testing using, for instance, the Spectro Fluid Scan handheld IR, which is quite a high value asset, but gives us a lot of information around the condition of the oil. So that can produce a go or no go, but there are costs involved there. We can do patch testing where we actually take an oil sample and provide a filter patch, and we can use microscopy. And there are other devices which can look at relative contamination, oxidation. There are field tests for tan, for water, etc., etc. Now, I'm not going to get into the solutions here, but there are many opportunities and options to do this. Now, what my view is here, because we've got a massive proliferation of sensors, we're using AI, we can use an off-site laboratory, and I certainly wouldn't suggest moving away from that. We can also do stuff on site as well, and we can gain knowledge about our equipment, even if it's very basic knowledge. We take a very small sample and we do some kind of qualitative assessment. This is good sense. So we're managing the risk, we're not just ignoring it. So any system managed by a calendar leads to unknowns and represents a risk. I recently went to a company and they said, we don't change oils, we don't have problems with gearbox failures. And when we dug a bit deeper, they were just used to doing refurbishments at a frequency which I would have considered to be excessive, but that was business as usual for those guys. So you may or may not know you've got an issue that you can improve on. And we tend to manage risks we're aware of by over-maintaining, and in doing so we introduce more risk. And if we take a component out of service to do something to it, we put it back into service, we actually create a new infant, and therefore because it's now a new asset, we're introducing a new risk because it's further down what we call the PF curve, where the potential for failure is increasing simply because we've actually taken it apart and put it back together. So the argument here is working smarter, not harder, and certainly not deferring without any understanding of risk. So we need to have the knowledge in order to make the decision. Now, we've done some work on a number of sites, and we can report quite confidently that there's likely between a 10 and 30% reduction in oil consumption, which at the moment is quite a critical thing to talk about based upon what's going on in the world and the knowledge that we're going to have supply issues, not only from the base oil and the refineries, but some of the finished products are going to be hard to get. And you'll probably have seen some messaging from any distributors or oil companies to say that pricing is going to be impacted. But we're also going to see potentially a reduction, and quite a significant reduction, in the lubricate-related work orders, i.e. stuff we do because it's in the schedule, but we could argue we probably don't need to do it. And therefore, if we're not getting involved with those assets, we've got fewer contamination-related failures, and we've got actually more likely that we're going to adhere to the schedule because we're going to be doing stuff which is relevant. So why does this matter? Well, the standards of our operations influence behaviour. And if anybody's ever done an assessment of any company's lubrication management, they will be very soon realise that it's the culture of lubrication which is often at the fault. Not necessarily individual fault, it's a corporate culture around lubrication management where it's been effectively flattened and forgotten about, and it's assumed to be running within reason. So what we have to do is we have to make sure that we don't see task deferral, i.e. delaying maintenance, as some kind of form of negligence. We can defer if we have the knowledge. We have to improve the reputation of lubrication and see it as good engineering practice, not just something we have to do which is given to those within the organisation with the least training and the least skill. We have to extend intervals with technical justification, and we have to make oil changes based upon the critical needs of the asset, not the need of the schedule, because the schedule is simply there as a smoothing tool and very often leads to greater levels of work. So why does this matter? Well, if you're using fixed time-based intervals, there is no relevance to the need of the asset. This is simply a tool to make work planning easier. It doesn't necessarily give you any value. If we're looking at OEM guidance, for instance, when you look at the handbook, they'll say perform an oil change every 70 miles or 70 hours or whatever. And I would argue that if you're taking an industrial gearbox, the amount of potential context that gearbox can be put into is going to be much more significant than the handbook's going to really relate to. So the handbook, in many ways, protects the manufacturer from negligence because it can hold its hands up during warranty and say, you didn't follow our instructions. But out of warranty, it has no value. So actually, maintaining the condition of the oil is very much relevant to your operation and your condition. And that may mean changing it more frequently or actually less frequently. The problem with schedules, again, it's very much focused on convenience. It's about the planning aspect, not necessarily the needs of the asset. And when you have something which is not based on the needs of the asset, schedule compliance, which is very often a metric that we use to measure how good we are, has no relationship to the reliability. It means you've done something, but it doesn't necessarily mean you've gained any benefit. And these, I think one would argue, historically were very sound views, but this now is changing because we can access more knowledge and have the ability to make better decisions. So what costs happen? Well, we have to pay for labour, we have to take the asset out of commission, we've got to manage any spills and contamination, we've got to expose individuals to health and safety issues, we've got waste, we've got potential errors due to human errors and perhaps training issues. And of course, we're now focused on work that is not rewarding us. We're focused on work which is simply a scheduled compliance task, creating unnecessary work, unnecessary costs, and unnecessary risk. So instead of seeing an oil change interval, why not make it a decision window? This puts the power back into the engineer and the reliability management in actually to do something that adds value, or to avoid it in the knowledge that risk is still being managed. So when we're using a decision window, when we get to the prize, we can define the acceptance limits and alarms for every system. We make decisions based on evidence as opposed to simply because it's time to do something, because it's the 4th of June and that's what we do on the 4th of June. We've got a clear authority to defer and extend oil change interval with time and date stamped verification of status, which gives us a feedback loop to confirm these decisions are safe. And we have confident knowledge of condition. Now, one real-world example, which I can quote, was a large refinery over in the States, and they were very diligent in doing their oil changes. And the scale of it, as you can see, was quite significant. And what they did a cost analysis by using the spectrofluid scan device, which allowed them to visit each sump, take a very small drop of oil and assess the oil condition, go, no go, etc. And in the first year of the trial, they actively identified that 90% of the systems did not require oil change. Now, over time, that number will drop because oil will require changing at some stage. But they actually avoided oil change on over 2,000 systems. And their calculation, not mine, was actually quite significant in terms of the first year. And they recovered their capital investment also quite quickly in that period of time. Now, noting that that capital is probably going to need replacing in 5 years, they've got 4 years of access with the only cost being actually taking the sample. Their prediction long term is to permanently eliminate 50% of the previously scheduled oil changes through a condition-based decision making with appropriate risk management. And they are now mapping this out to other sites. Now, admittedly, this is a large group of assets and that may not be relevant for everywhere. But the process suggests that at least we should ask the question, is there an opportunity to move, maybe not all of the assets you don't put in an oil condition monitoring program, but some more assets into that so we can avoid unnecessary oil changes. So I'm coming to the end of my 20 minutes. My key takeaways are schedule oil change feels safe, but they add cost, and we can see that cost can be quite considerable. Condition data, if we can acquire it and trend it, adds a degree of certainty to our decision-making processes. And this new activity does not necessarily require any significant training or upskilling. We use very competent people generally, and giving them the skills and awareness to take lubrication to another level is quite straightforward, so long as it's built into the culture. So we also get value from avoided work, the risk reduction, and the added assurance that we are actually working based on data and intelligence. And as you've seen, the value can be significant for medium to large size asset populations. And that ends my discussion today, and I thank you very much for your attention. Please, if there are any questions, we'll get round to it in the panel at the end. But for now, thank you.
Thank you, Danny. You have had a question come through, so I've made a note for that for later on. Condition-based lubrication is something which people are adopting more across all industries, and as you've shown, sometimes doing too much can cause problems, even in the smallest of oil or grease reservoirs. Understanding the condition is invaluable for improved reliability and sustainability, especially in this time of worry with lubricant supply. We certainly don't want to be changing oils and greases just because. Thank you everybody for your concentration. We'll now be taking a break for 15 minutes and I look forward to welcoming you all back in around 15 minutes time. So we'll say at 10:55. See you all very soon. Welcome back everybody. I hope the short break was enough time to recoup, ready for our next presentation from Gwyn Simmons of Polaris Laboratories. So Gwyn has worked in the fluid analysis industry for over 25 years now, almost a lifetime. From testing in the lab, data analysis and interpretation, to technical support and sales. So he really has seen all sides of the lubricant reliability scene. He's based in the UK, however, he's always jet setting as he's got a global responsibility for sales and marketing at Polaris, supporting customers at their 8 global laboratories. He works with some of the largest manufacturers and end users globally, showing the value that oil analysis can bring to their businesses. Gwyn also supports these customers on program optimization and using data to improve lubrication and reliability practices. Gwyn's presentation will talk us through how to stop using oil analysis as a tick box exercise and really make use of the big data to overcome lubrication issues on site and lubrication wastage, something that a lot of people are dropping chats and messages in about at the minute. So thank you for joining us, Gwyn. We can see your presentation and your 20 minutes start now.
Thank you very much, Jade, and good morning again to everybody here. So yeah, as Jade said, my session here is kind of going to look at the data angle. Obviously, we've seen a couple of great presentations from Adam and Danny kind of on the testing and things like that, but which may rely on the output, but I'm going to kind of concentrate on how important the input of data and data management and program management is as well. So probably not the first thing you'd expect to see on a webinar this morning on the benefits of lubrication management and oil analysis. So a phrase of oil analysis doesn't work may be a surprise to you. But this was essentially a statement that was delivered to me by one of our customers last year based on some issues they were having, based on some issues they've had, and saying simply oil analysis does not work. Now, as Jade said, I've been in this industry for a lifetime, over 25 years, and this is all I've done. So for someone to say that to me directly kind of piqued my interest and say, well, why does oil analysis not work? What are the problems you've been having? So with anything, we kind of want to peel the onion back and find out what the actual problems were. So we engaged this customer, we visited them and said, well, you know, why is your perception that oil analysis doesn't work? What are the issues you've had, or what are the issues you've seen with oil analysis in general that is giving you that perception that it's not the right tool from a condition monitoring standpoint for you? So they essentially said we had a problem with a piece of equipment. So there was either some abnormal noise or heat or some other visual or audio issues they were having with this particular piece of equipment in their plant. They took a sample because they knew they were having operational issues with it, and they sent it to the lab. Now, we tested the oil and we sent the report back to them, as most off-site laboratories will do. The sample came back green or satisfactory, whatever you want to call it. So they assumed everything was okay. Literally the following day after they received that report, the unit failed. So they then followed up with oil analysis doesn't work. If oil analysis did work, it would have informed us of the problem. We may have saved or done some remedial maintenance on this piece of equipment to find the problem before it failed catastrophically. And oil analysis should have and could have given us the information and informed them of what that problem was. They also followed up with, in fact, there's been a number of issues over recent years, not just with Polaris, but we transitioned to Polaris from a previous provider a couple of years ago, and there have been other issues where oil analysis has not picked up problems with pieces of equipment. Now, we all know from an operational standpoint, you can get catastrophic failures, which oil analysis may or may not pick up. But they had a general perception that it was potentially a waste of money. Now, was this because they were just paying lip service to it? Was it something they do because they've already done it? So again, it's important to find out the fundamentals of why this is their perception of oil analysis. And this was the report we provided back to them. As I said earlier, they look at the sample report and look at the top of the report and go, it's green, it's normal, no problem, we don't have to do anything. You know, the lab guys are the experts, they've sent us a report that said everything's okay, we don't need to do anything. But if we look at the report in a little bit more detail, so as I've said, the operator, the guy receiving the sample reports, just looked at the top of the report and said, it's green, it's normal, we don't have to do anything, we don't need to make any decisions because the lab's told us it's normal. But on closer inspection, you can see here in the equipment information that we didn't know what the oil was. They provided no information on the system type or the application or what piece of equipment or machinery that sample was taken from. They didn't provide us with any lubricant details, so they didn't give us the lubricant manufacturer, the product name, or the grade as well. If we go back to Adam's presentation, what's the most common type of oil we test? Unknown. And this is an exact example of that. So it doesn't give us as the lab any information of what we're working with, what we're trying to recommend as well. And if the user had actually read the comments on the report and able to provide accurate recommendations as limited information is provided with the sample, in order to accurately interpret these results, please confirm component type, so the piece of equipment, the manufacturer of the model, along with the lubricant details in use. Now, if that user had read those comments, they may not have made the decision not to do anything with this piece of equipment which failed the following day. If they'd have read that in more detail rather than paying lip service to, we've taken a sample, we've sent it, there's nothing wrong. So understanding what information is on the report is just as important as looking at the overall severity as well. So really, the problem lied with the information we were provided by the operator, by the end user, with this particular individual sample from this equipment that fundamentally failed. So for the rest of this session now, I'm going to explain that oil analysis does work, and here are some of the solutions based on providing accurate and informed data to the laboratory when sending samples in. So what is the solution? Well, firstly, we need to take a step back and do a complete review of all of the data related to that program. And that is the asset lists, the equipment lists, all of the information that's relevant to the lab when testing and interpreting that data related to that piece of equipment or those customers' fleet of machines that they're taking samples from. It's also important from time to time to review the test packages or test suites that are performed on individual samples, because again, they may or may not be as accurate in terms of the contamination, which Dimitri will touch on after me, that we're trying to find, or the things like the fluid condition or the lubricant condition as well. And then obviously now we're living in a technology world. You know, what technology is available to oil analysis or fluid analysis users to enable them to get as much out of the data as possible. Yes, the individual sample report is important, but trying to kind of have that macro view of the data is becoming just as important in today's day and age as well. So if you kind of peel back and go through these issues or perceived issues with the customer, then it's important to document, update, because going through a whole exercise of improving the program today, but then nothing is documented, no processes or work instructions are written moving forward, most likely you are going to be in the same place in 12 months' time, in 2 years' time, if those documented processes aren't adhered to, and working closely with your laboratory provider to work together to that continuous improvement loop with all the samples you take and the actual management of that data within that program as well. So if we look at the testing, now we asked this customer, why are you doing, the tests you do? And they said, well, it's what our previous provider did. So we just assumed, assumptions can be dangerous, that these are the best tests for these particular applications on compressors, hydraulics, and engines. So we actually said, well, during this RFQ process, we advised, additional testing more related to the equipment you were testing. And they said, yeah, but we wanted to keep the costs down. So they were seeing an oil analysis sample as a commoditized service rather than the wider kind of lubrication management, something that Danny touched on in his session. So we've said now, well, if you're experiencing some failures and you're not getting as much information or accurate information from your program, can you see sometimes that these packages may not be working? And they said, yeah, we hold our hands up, we can see that. Then essentially what we need to do is review what tests we're performing. and a couple of the kind of low-hanging fruit where they weren't performing water content in parts per million. They were just doing a carte blanche percentage across the board. Now, if the percentage is via a hot plate method or an FTIR, that really hasn't got the limit of detection to go down to maybe 200 or 400 parts per million, which could be the condemning limit for water contamination in some industrial applications. And more critically, they weren't doing a ferrous debris test on their gearbox oils, which again is vital to understand, is there any larger ferrous or iron wear patterns occurring in those individual gearboxes. We then looked at the assets. So this was their asset list. And we can see there, again, similar to what Adam said, there's a huge amount of missing information. This was their asset list. You know, we've got one manufacturer, we've got no models of the equipment, we've got 3 fluid manufacturers. Yes, we have the fluid grade, so we have something, but I'm pretty sure there's more than one product, which is a mobile ISO 46 hydraulic oil. There's probably tens, thousands out there. Also, there's tens of thousands of ISO 320 gear oils. They didn't give us the manufacturer, they didn't give us the model. So additive levels, specifications, formulations all differ. So having that information is critical for us as a laboratory to provide the most accurate information in there as well, because that not only affects the interpretation we provide and the severity of the report, but also the comments and recommendations we would make and the limits we would use based on certain applications as well. And why is that important? Well, if we think of what information a laboratory uses with a sample that comes in, you obviously have the laboratory test results, which are derived on the samples as tested in the lab. You have the equipment type. Now, it's important to say, what kind of engine is it? Oh, we've sampled an engine. Okay, is it a diesel engine? Is it a petrol engine? Is it a dual fuel or natural gas or landfill gas engine? So having that exact type of equipment is important. You know, what type of gearbox is it? Is it a kiln gearbox? Is it a conveyor gearbox? Which all have different applications, different duty cycles, different loads. So having that exact equipment type application, again, is critical for the most accurate interpretation of an asset. You know, as I said on the previous slide, the information on the fluid manufacturer, product and grade, as Adam pointed out as well, is vital for the laboratory to interpret against the correct viscosity, but also the correct additive levels and formulations to ensure that the oil and the lubricant in use is exactly as it should be, as taken out the barrel from the lubricant provider. And then obviously component manufacturer and model. You know, there are tens of thousands of different engine manufacturers or compressors manufacturers. They all have different metallurgies. They will all wear at different rates as well. So having that definitive information on the manufacturer and the modeling of the equipment is critical to ensuring the correct statistical models are used for things like wear and contamination levels. And then obviously finally the application. A gearbox in a clean, dry fulfillment center, for example, is going to operate very differently to a gearbox in a cement plant where you have, very dusty airborne contaminants which can affect the operation of that gearbox as well. So the type of environment the equipment is working is also a critical factor in terms of what limits are provided, how the interpreter looks at that data to provide the accurate, because without any of this information, we could provide, erroneous information. We could flag things too early. We could miss flags because that information is not provided to us. And all of that kind of gives the overall severity of the report, but also, as you see there, where certain tests or certain data sets from the laboratory are flagged, green through to red, depending on the criticality of those results, based on all of this information that the customer, should and needs to provide. And there was a comment there which kind of ties into this slide in the chat about, well, what are the limits? How do we know what's right and what's wrong? We have a data set of over 25 years of data with over 21 million samples in that data set, which allows us to have 50 million individual flagging points and over 55,000 flagging templates. And that is based on differences in the manufacturer, the model, the lubricant grade, the lubricant manufacturer, the application as well. So we probably have the largest data set of oil analysis statistics, which allows us to confidently predict and flag certain data sets in there as well. Now, if the customer provides us with no information, we can just do a very generic interpretation based on it's a gearbox. these are a typical data set or statistical analysis of gearboxes. But the more information the customer provides allows us to drill down to a much more accurate statistical model in terms of providing that interpretation and recommendations. So if we think of how important, that information coming into the lab is, how do we fill in the blanks? So if we take an individual asset, which was the one where they've said, we had this impending failure, they didn't give us any information. You can see there that the manufacturer, the model of the equipment was missing, and they give us minimal information on the fluid type. But once they reviewed and actually went through their records and found out the manufacturer, the model, and they've actually said, we know it's mobile hydraulic oil M in use, it gives us a much more better information of what is in use in that equipment, and we can become, or any laboratory can become, much more prescriptive in their recommendations and flagging for that customer when that information in there as well. Now, Danny touched on AI. Now, AI is becoming, very prevalent in our industry in terms of customers extracting data, putting them into their own data sets and own data models to look at predictive analytics and models. Now, AI is only as good as the data set that feeds it. If you have a data set where most of this information is missing, the output from the AI agent is going to be significantly less powerful compared to where you have a full implemented asset list with full manufacturers, full models, full details on the lubricant information here as well. So the customer went through a process of finding out all of this information, kind of filling in the blanks, sending that over to us to provide then a much more accurate interpretation moving forward on their samples and on their sample reports as well. If we go back to that problem, they sent a sample in, they gave us no information, we couldn't do any interpretation because we didn't know any information on there as well. They filled in the blanks. So if we go back to the original report we saw on one of the earlier slides, unknown oil, unknown lubricant, the laboratory is unable to provide accurate recommendations without this information. If we look at the same report, now the customer has provided us with that, vital information, we know it's a hydraulic. We know the manufacturer, the model, and they've confirmed the product in use as well. We can now make a much more informed interpretation and recommendations just based on that additional information they've provided. And you can see here that a lot of the data is flagged. So there's relatively high levels of iron, there's levels of contamination, and it's clear to see that the additive package in this particular sample, is very different to what we'd expect in this hydraulic oil. So clearly someone's either topped up or used the wrong oil, and therefore our interpretation details that it's the viscosity and the additive levels aren't consistent with the stated product. We found ferrous wear, which could be coming from a variety of sources within the system, and the overall severity of the report is now red or critical or severe, which is a marked difference to the original report where we said it was green because everything was normal. So even if they didn't read the report or didn't look at any information and all they did was look at that top right hand corner of the report, they would have seen it's red. Oh, we need to do something. So even if you're not paying in-depth attention to this, just the visuals on the report with that additional information would have led them to a problem with this particular piece of equipment that they needed to rectify, hopefully before it failed or was about to fail in there as well. We put all this in place. The customer says, right, we want to keep everything clean. We now believe in oil analysis. We want to keep this kind of consistency moving forward. What are the best options? Now, a lot of labs now have a mobile app, and the mobile app can be used for sample submission. So the engine to transfer sample information at point of application of sampling to the laboratory. And just think how clean and accurate this is compared to a historical or traditional handwritten form where customers handwrite the asset ID and the information. They could miss information on here as well. Whereas with the electronic submission, it's very quick, very easy to put the component time, the age of the equipment, the age of the fluid. Was the oil changed? Yes or no? Was the filter changed? Yes or no? Quick and easy, takes about 30 seconds to do, put a QR code on the bottle, and the lab gets that accurate information. What they also prevents as well versus the traditional paper version is duplicate IDs, loss of historical trends. So really moving forward to keep the data set as clean as possible and future-proof it, electronic submission really is the way forward compared to traditional handwritten now, and probably about 60-65% of our business globally uses electronic submission, which is obviously good and good for the environment because we're providing less paper to customers as well. If you've got good data sets, as I mentioned before, from kind of an AI output, it also allows the labs to perform better data analytics. Now, if you have minimal information on manufacturer, sample type, lubricant, you can't really do that high level macro data analytics on the complete data set. Now, this complete data set could be for one location, or it could be for a multinational company who have multiple locations nationally or globally as well. So you can compare like for like with manufacturers, models, different types of lubricants and different kind of systems as well. So having that complete data set really does allow you to perform things like Pareto analysis to see where that low-hanging fruit of potential lubrication problems are with your fleet of equipment. And in terms of the current status, as Danny mentioned, several times in his session, are we changing oil too early? Now, you can't really determine how good the lubricant is without sampling, without testing. But if you have accurate information on the sample, on the running time, it allows you to perform scatter plots and scattergrams to see, right, well, what is the condition of the oil over certain time periods? We change the oil at 500 hours. Why? Because that's what the OEM says. That's what the fluid manufacturer says. Well, if after 500 hours, all of the oil condition parameters are still at a satisfactory level, there's no significant contamination or wear, then really it does allow you to safely extend or optimize your drain intervals, which could become apparent in coming weeks and months across all of your lubricant products, purely based on the data that the laboratory provides. So to conclude, oil analysis does work, but it works best when complete information is provided to the lab on all samples. The information provided by end users to the lab directly reflects the flagging limits, but also the recommendations and the overall severity of that sample report. One-off samples, like in the problem at the beginning, can help, but really routine, regular samples provide a much clearer picture of the condition of the equipment and lubricant, as the labs are able to trend and compare samples over time from historical statuses. And really, oil analysis programs are a partnership between the operator and the lab. Yes, the labs are suppliers, but when you have that two-way communication and working together, really does benefit the program as a whole. And just to confirm, my opening slide, oil analysis does work. Thank you very much. And I think we have any questions at the end. Appreciate your time this morning. Thank you.
Thank you, Gwyn. You've got several questions in the chat if you get time to respond to them. Data is so important now more than ever. The more information that we pour into a system, the better, as you said, with AI up and coming, especially in our industry. The filling in the blanks section that you covered shows the power of a good communication stream between the lab and the customer. Simple information, which is sample specific, also helps. It was raining when I took my sample, the temperature was much higher on the machine as usual, and the breather's saturated. So thank you very much for giving people an insight. I hope everybody is ready for a scientific fairy tale. Our next speaker is Dimitri, and he will celebrate his 20th year at Swansea Tribology this year, racking up almost 2 decades of experience monitoring lubricant and asset condition. Dimitri holds a PhD in mechanical engineering, which allows him to see all angles of the asset life cycle while supporting his customers with their oil analysis programs. Dimitri oversees the laboratory operations at Swansea Tribology Services and will today open our eyes to fantastic contaminants and how to find them. Dimitri, I can't wait for this any longer. Thank you for joining us. We can see your presentation and I will hand over to you now.
Thank you, Jade. So, why do we want to talk about contamination? Because it can cause problems in our lubricants and therefore in our machines. So what are some of the issues that contamination can do? It can stop the oil from performing its key function. Adam spoke about viscosity, how important it is. Many contaminants are actually affecting the fluid, the bulk of the fluid. You can have fuel ingress, water ingress, ingress of a different lubricant with a different viscosity grade, and that can lead to a change in viscosity, and it can stop the lubricant from performing its key function. And there are other functions that can be affected, things like demossability, ability for lubricant to separate from water, air release. There'll be issues with corrosion control, hydraulic performance, temperature control. Contaminants can corrode components, and a lot of the times when we talk about contaminants, we also mean particles, where debris becomes a contaminant itself once it's generated. So those can act as an abrasive medium, increasing wear. And contamination can also cause filter blockages, which can then cause oil to go through bypass, and just cause all sorts of problems. And generally, a lot of machine failure is caused by poor lubrication, and contamination is a significant contributor to poor lubrication. So I'll speak about how we might want to look at contaminants. So by maybe categorizing them in different ways, and each of those will give us a different perspective. How we can detect contamination using a lab to identify the contaminants, what some of the test methods that may be used, and give a few case studies, a few examples. Generally, it's a bit like CSI, but unlike on TV, we're grounded in reality. So we may need to use different test methods for different types of contaminants, and we have to deal with the quantity of material available and the cost of analysis. So if we split the contaminants by phase, so one of the main phases is the solids. So we have sand and grit particles, wear debris is generated within the machine, but it becomes a contaminant immediately after that and can cause further wear. Things like rust, soot in engine oils, paint chips coming off the different surfaces within the equipment, maybe the painted surface of a tank. Various process materials, powders, fibers, either environmental or from filter media breaking down. You can have degraded elastomers, hoses and seals, and oil itself as it degrades. It forms degradation products, varnish precursors. They may be soluble to start with, but they form insoluble particles which can deposit as varnish and lacquer, can block filters and so on, and they become another contaminant within the system. Looking at liquids, one of the most common contaminants is water, but you also have things like fuel, coolant, AdBlue, using an incorrect lubricant, topping up with an incorrect lubricant, that's a contaminant as well. And when we get the first sample, if the lubricant grade is unknown, then the oil that's already in the system may effectively be a contaminant because it may not be performing its rightful function and may need to be replaced. But also process fluids and maybe detergents used to clean the area and then getting into the system. You also have gases, things like air, refrigerants, so compressor oils so have a lot of refrigerant gases coming in, maybe fuel, steam, vapor. Yes, it condenses once in the oil, but it's a gas sort of coming in, and then various process gases. So whatever it is that you may be compressing, you'll be using your compressors can be getting into the compressor oil and causing issues. So we can also break contaminants down by chemistry. So we look at organic contaminants, so various fluids, oils, fuels, various process fluids. We're dealing with hydrocarbons, they are organic products. grease, fibers from filter media, sort of cellulose fiber or organic material, various plastic or elastomer debris from O-rings and seals and hoses, and organic in a different way, but biological contamination. So when we're looking at diesel fuel, for example, we can get diesel bug, but also that's something that can come into lubricants, especially when there's a lot of water present, and that can cause problems because there will be sludges and sort of contamination that can clog up filters as well. Inorganic contaminants, so a lot of it is particles, sand, grit, wear debris, various process dusts, other inorganic debris. And we can look at aqueous contaminant as being sort of a separate class on its own. So water, coolants, AdBlue again, various detergents like screen washing and vehicle application, various water-based process fluids. And all of those different chemistries require different approaches, different techniques to detect them and identify them. We can look at contaminants by origin. Is it something that's coming from within the system, be it wear debris, breakdown of like hoses, oil itself breaking down the degradation product from oil? It could be external, things like water, fuel, coolant, dust, dirt. Adding an incorrect lubricant, it becomes a contaminant. And another way to look at contaminant is by concentration. Is it bulk contamination? You know, we have 10% fuel in this oil. Is it a mixture of different lubricants? We have 50% on one lubricant, 50% of another lubricant, a lot of water getting in, or is it, and those are often obvious. There are significant effects on many properties, but also sometimes you can visibly see two layers within the sample, where at the bottom you have maybe a layer of water or a layer of different lubricant that has different densities, so they separate, so things can be obvious. But we sometimes need to look for contaminants which are present in very, very small quantities, concentrations. So trace contamination, this can be wear metals, moisture again. Some systems are very sensitive to water content, so being able to detect it at a very early stage, at very unquantified, very low levels, like we were saying earlier, parts per million rather than percentages, and sometimes even 70 parts per million in an application may be considered too high. But also ingress of additives as an indication for different lubricant getting in, and the varnish precursors as well. They're present in small quantities, but they can cause various problems. We can look at contaminants by rate of ingress. Is it gradual? So normal wear particles, maybe water ingress through condensation, slight coolant leak, the degradation of oil, the buildup of the insolubles, soot buildup, and then ingress of dust and dirt, perhaps through breathers which don't have this filtered breathers on, or it could be rapid. So unknown water contamination event, somebody was pressure washing something and lots of water got in straight away, or there's a head gasket failure in an engine, or somebody just put in correct lubricants top to top, and immediately we have a bulk change, which is very rapid. Ingress of dust of dirt and dirt in a more rapid way, or severe wear event which generates a lot of wear. And then we can look at it by severity of impact. There is some contamination which is going to have moderate impact, slight impact. So things like normal wear, it will build up. It may start becoming a problem by itself, but it will take time. A moderate fuel dilution, we're detecting a contaminant, but it's not causing a problem yet. It's very gradual ingress of fuel, for example, gradual buildup, or addition of a lubricant that's actually a compatible lubricant can work with a lubricant that's already in the system, and we may detect it and we may decide actually we know that it's okay, or we may perform a compatibility study and confirm that it is okay so that we are sure, and then carry on. But you can have critical impact as well. So severe fuel dilution reduces viscosity, can cause rapid wear of your engine, severe ingress of water or coolant. Again, the lubricant layer is broken down, oil is unable to carry the load between the loaded surfaces, and you can have critical consequences of that. And high quantities of particulates getting in, again, that can act as an abrasive component, causing severe wear and rapid failure. So how might we detect contamination? There may be a known contamination event. Somebody thinks, oh, I may have put the wrong oil in, or we know we have pressure washer. They used a pressure washer in this area. We know water is likely to get in, or there was a leak in the roof, and we know water was pouring down onto our piece of equipment. Maybe visual inspection, either of like through an oil side glass, we can see there's discoloration, we may see there's cloudiness, we may see there's changes in appearance of oil, or we may see contamination on the surface of the equipment, or we may see that actually there was a we can see that the hatch to the oil tank is open, and this will likely allow some contamination to get in. There may be operational parameters where you may be monitoring temperature, noise, vibration, pressure, various other performance parameters, and all of that may change, and that change may signify, may be caused by ingress of contamination. You may not always know about it, but it may prompt you to, okay, let's find out what's going on. And then another potential avenue is through routine lubricant analysis. Either the lab has detected contamination directly, for example, increase of moisture, increase of water content, or we notice the change in property, viscosity, or perhaps the emulsibility, air release, something that can be affected by contamination, and then we may want to investigate and find out what the actual contamination is, but we have detected its presence in an indirect way through a property change. So if you are using a lab to identify the contaminants, often we have customers come to us with one tiny sample of something and say, oh, can you find what the contamination is? Oh, this is the contamination, what is it? And there is no context, there's nothing to compare to. So they come to us sort of when they're desperate and they want to find something out and they have taken some steps. It would be great if they involved us early and spoke to us about, well, what is the best way to investigate this situation? So when you send a sample to the lab talking about contamination, you may give your suspicions, or we think it's that, but remain open-minded and allow the lab to suggest test suites, which may do an overall condition. We had a sample come in where a client was wanted to check if there was AdBlue in fuel. We got that fuel sample. Normally fuel is, fairly clear liquid, maybe slightly yellow or slightly red if it's red diesel and so on. It was black. We tested it. They allowed us to perform the standard test package rather than just looking for AdBlue. So for reference, if there's AdBlue contamination in fuel, if it's significant, there's normally a layer of separated fluid at the bottom of the jar, which you can then test and find out if it's water, something else, or if it's AdBlue. There was no separation there. Sample was black. When we performed the routine analysis, we found those trace engine oil additives and a layer of black sealed, likely soot contamination. So it looks like there is engine oil getting into sooty engine oil getting into the fuel, and that's something that the customer can investigate, but it was not in line with the initial assumption of AdBlue. When you perform an investigation, you may want to find out not only what is the contaminant, but also where is it coming from and how is it getting in. So this is where deciding what samples to take, where from, how to take them, you may be able to narrow down the point of ingress for the contaminant, But also, as you're listening to and looking at these presentations, you're in a position where you could afterwards take steps to prepare yourselves for when you may need to identify a contaminant and do some sort of investigation, because you want to have to hand some clean oil sampling bottles rather than a rinsed out coffee jar or a lemonade bottle, cola bottle, and so on, which immediately introduces a question, well, the water content we're finding in the sample, is it contamination of the sample, or is it because you had no suitable oil analysis container available and just used whatever was to hand and you rinsed it and it wasn't dried properly? And then you want to take into account how much sample you're able to provide. You want to collect as much as possible, because different tests looking at different chemistries, for example, may require different quantities of sample, or if you test on certain properties. So another question is, can the sample be isolated? Can you isolate the contaminant, or is it contaminant that's present in a sample of oil or grease or whatever it may be? And then ideally you want to supply, so if you have isolated contaminant, ideally you want to supply a sample of oil, bulk oil from the system, because that will give context. And if you can supply a sample of virgin oil to be used as a reference, or samples of candidate contaminants, if you say, well, we think there may be incorrect oil being put in, these are the lubricants we have on the site, so we can supply you samples of virgin oils of other grades which are present. So discussing then what tests may be used, there are some tests that everybody who is at all familiar with oil analysis will think of straight away and go, oh, can we just get that done? But speak to the lab, describe the problem, ask them if there's anything else they can recommend, and sometimes there may be multiple tests which can help isolate a contaminant, narrow down, and confirm whether it's this or something similar, and it's useful to discuss things like that with the lab. Sometimes the lab may be able to prepare a sort of synthetic reference, simulate the contamination. So if you think there's so much of this product getting into this product, if you supply those neat products together, we can mix them and then compare with the sample, the unknown sample, and see, is this similar to that mixture? And if in some situations it's not always possible to fully understand what the contaminant is, you may, however, be able to eliminate a lot of other things and decide and understand that the contaminant is not this. It's not this lubricant, it's not this grease, it's not detergent fluid. You could also use this opportunity to assess the condition of the oil, whether it is still good, whether it's still able to perform its function, even though there is a degree of contamination in it, but the contamination that's present may not affect the key properties. You have detected something, maybe it's a compatible lubricant. You could talk with the lab and decide on further steps of how to continue the investigation. So, as I said, if a lubricant is being added in and is deemed a contaminant in the initial instance where you don't know whether it is going to cause any problems, you could perform a lubricant compatibility study and then determine, yes, actually they are compatible, they are fine to use interchangeably, or we may prefer to stick to one, but if there is a disruption in supply, we're able to use this other lubricant, and it's not a problem. We don't have to immediately drain oil, lose hundreds of liters of oil, and then refill it with a proper lubricant once it's back, because the lubricant that we have is actually acceptable. So moving on to a few tests. Visual appearance and color may be indicative of contamination. Viscosity can help detect fuel dilution, incorrect lubricants, process fluids, degradation of oil, oxidation, for example, cracking. Flash points for detecting fuel, gas, incorrect lubricants sometimes. Density, different lubricants may have different densities, different process fluids and fuel. Water content can be detected directly by Cal-Fisher titration or crackle hot plate infrared and so on. And then elemental analysis using either ICP or a rotating disc electrode, looking for wear metals, additive elements, contaminants. Particle count may help detect ingress of particulates, but it's also useful to separate the more solid contaminants, or sometimes sludges, fibers, and so on, onto a filter membrane for further examination, either microscopic, and you're able to see quite a lot of difference between the different contaminants. You have some sort of copper-based wear particles, and you have cotton wear particles. You have some fibers from filter media degrading. You can get a lot of information from just looking at the contamination. And you can also then use things like scanning electron microscopy, which is very good at analyzing the elemental composition of individual particles, of particle population. So you can find out that we have 30% of the wear debris is of this metallurgy, which leads to a particular component. 20% is of a different metallurgy, so there's another component that's also wearing. And this works for inorganic contaminants, wear debris, that sort of thing. Another useful method is infrared spectroscopy. This works best for organic compounds. The spectrum that's produced is indicative of molecular bonds present in the sample. When samples are a mixture, it may be possible to isolate the samples and test each component individually. But we also have access to previously tested samples, library spectra, and can also not only identify a contaminant, but we may be able to exclude certain contaminants. So as a case study, we had a customer come in with some fibers that we found in the oil system. They brought us some rags and some spill kit, and we were able to perform analysis and identify that the pad material was a match to the fibers and the other material was not. So they were able to then identify where the contamination is coming from. Another case study, we had suspicion of seal oil getting into the lubricating oil. We performed infrared analysis, some other tests, and they have provided us a sample of virgin oil. And we found that the virgin oil sample that they have provided us was not matching the expected grade. And that's why the viscosity was different. So we use infrared spectroscopy as well to check the contamination, the concentration levels of prepared text mixtures of lubricating and seal oil. We were able to predict it with high degree of accuracy, and we were able to confirm that actually there was no seal oil in the lube oil, and that the fault was entirely due to an incorrect lubricant being used. Another example of detecting contamination through a property change, we had an oil sample where after a long time of good demulsibility performance, we had a sample with poor demulsibility. So instead of demulsifying after 210 seconds, after the 1200 seconds, there was still 5 milliliters, there's only 5 milliliters of oil separated. We repeated with follow-up sampling just to check, make sure there's no issues. And the result held. And one of the things we noticed was very low levels of calcium and silicon in the system. And demulsibility of oil is a property that can be sensitive to very low concentrations of certain contaminants. So this information gives the customer a chance to investigate, find out where the contamination may be coming from. But it's not just about finding out what the contamination is, it's also finding out what you can do to deal with it. And in this situation, whether this property is critical or not, because demulsibility is important when there is water getting in, but if you have very good controls of moisture levels, no water getting in, you may be able to continue with this condition where demulsibility is not ideal. So we saw, as I said, a little bit of calcium and a little bit of silicon, which initially did not strike us as particularly high and abnormal, but once the problem was confirmed, we investigated further, and that was a possible cause for the demusibility problems. And then finally, when a lab is trying to help, they may be able to give you advice not only on what the cause of something is, but sometimes a solution. We have spent some time investigating a situation where some waste oil was turning into a solidified gloop, which could not be used, and then it became very expensive to dispose. Whereas when it stayed liquid, it could actually be used as a supplementary fuel in coke ovens. So we have performed a lot of testing, and we just could not identify what the problem was, whether it was specific contamination, whether it was just a different initial product coming in. There were just too many variables at the time. So with the clients, we were able to come up with a solution of adding some waste diesel, degraded diesel that they had available on site, and that allowed the fluid to stay liquid and stopped it from solidifying, and they were able to successfully use it as a supplementary fuel. Thank you, and I think we will be able to take questions as a panel later on.
Thank you, Dimitri. Just to let you know, you've got some questions in the Q&A to answer after the panel. Contamination is a contributing factor to a huge percentage of lubricant and asset failures across industry. So thank you for showing us the type of contaminants and the potential failure paths. I think it's really insightful for viewers to see how contaminants are identified in the lab and how the analysts turn that complex data into information which can be used to fuel maintenance activities. We've got all the panel members up now. So we'll move on to the panel. Thank you everybody for presenting today, and thank you to our viewers for the engagement in the chat and for staying online. We didn't lose any participants, which is always good. We'll not get time to answer all the questions, but we will follow up from this webinar with an email containing the contact details of all the committee members on the webinar today. So feel free to reach out to them to discuss any concerns or issues, and we will individually get back to all the questions that are in the chat. So we had a concern submitted, and I've decided to choose this one because I think everyone can relate to this, from the committee members through to the viewers and end users across industry. It's quite a long one, so listen in, panel members, because you're going to be answering this. So the concern was, I'm involved in a large maintenance and improvement programme, shifting from reactive and preventative to a CBM approach. We're a small team in a company with hundreds of assets. We're trying to learn about various CM technologies while also trying to revamp maintenance strategies. They've trialled oil sampling of gearboxes on critical assets. However, the knowledge of lubricants and lubrication is entry level. My biggest concern in relation to lubrication is lack of formal guidance within the business and lubrication practices that vary from site to site. This concern came in during Danny's presentation, so I'd like to pose this to Danny first, and then the other panel members please contribute. So Danny, their biggest concern, if you could help, is that they have got a lack of formal guidance within the business and lubrication practices vary from site to site. How can this viewer combat that?
Hey Jade, well thanks for coming to me first, as it kind of sits in my wheelhouse a little bit. Firstly, I'd applaud any initiative to look at improving maintenance and reliability in this way. I think asking the questions of oneself, should we say, is where we need to start. With every business that I've had the fortune to go and see, they all need some kind of external guidance, because they can only see from within. Now, external guidance can be by reaching out to a laboratory or looking online and getting information and building a story yourself. But I would say you need to set out essentially where you are and build a roadmap going forward. Now, I talked briefly about best practice, and I I believe there are best practice guidance. We have ICML, which is the International Council for Machinery Lubrication. They developed a standard called ICML 55.1, which is intended to align with the asset management standard, which is ISO 55000, but predominantly around lubricants, lubrication and lubricant management. So there's a particular framework you can look at, and that covers 12 or so areas of lubrication management, one of which would be oil analysis, for instance. And what I would heartily recommend anybody who's trying to move forward is to understand, as I say, where you are now and where you want to get to, and not necessarily aim to be best practice, because it could be too far. It could be a big mountain that, and really you want to take the next stage to get, if you like, the early hanging fruit. Now, recently I listened to a number of presentations, and they talked about getting a score, getting kind of score systems. And a number of places you can do that, looking at maintenance maturity. I know SKF do it, I know we do it. A number of consultants out there have the similar schemes where you actually basically go and create a site survey, or you go and have a business meeting, and you assess the various functions around lubrication, and you basically score what's being done well, and you look for opportunities to improve. Now, if you're looking, let's say, on a 1 to 10 basis, I would say if you come out and you score a 2 or a 3 early on, getting to 3 and 4 and 5, probably you're talking about doing the basics, such as sorting your stores out, getting your fluids cleanliness, knowing which grade you're going to buy, making sure you've had a degree of training and you've got some competency. But moving between 5, 6, 7 and 8, this is more about sort of how you document and manage the process of lubrication management. Because these are optimizations, and you may not need to get that far up the tree to get the return on your investment. And I'd also say there's no such thing as a 10 out of 10. It's always somewhere you should aspire to, but you should never arrive, because there'll always be another opportunity to improve. So, short answer, assess where you are now, where you want to be, and develop a roadmap to get there. Some of it will be training, some of it will be talking to oil suppliers, some of it will be about storage and handling, some of it will be about getting senior management buy-in. You know, there's a whole range of things that need to be considered. And using someone externally need not be a big cost. It need not be a major consultative exercise. It can simply be having someone to reflect on, someone who can sort of see it without the blinkers that you would normally have within an organisation. So that would be my response to that question.
Absolutely. Thank you, Danny. I know Adam mentioned in the chat about seeking the guidance and advice of the lab that you're currently using for oil analysis, and that's always a really good way of seeking some guidance. They maybe can't support with a full CBM strategy, but they can certainly support from a lubrication point of view. And if I can just quickly interject, I recently was on a working group call, not with the BINDT, and one of the users on there, he was really strict about his process, all the way through from procurement to kind of mobilising these maintenance activities. So that would help with your practices varying from site to site. Be really strict from what they can purchase, what they can use, and make sure that transpires to every single site. So there is a really strict system in place, maybe from the 55 standard Danny mentioned, and it's really difficult from people to stray away from that site to site. Other panel members, does anybody else want to contribute? Gwen?
Yeah, I just kind of, I completely echo what you and Danny have said, and Danny mentioned it there, which is a vital importance of, getting management buy-in, because a lot of time, if you're coming in trying to change things, and it might not be just oil sampling, it could be vibration or thermography or other condition monitoring techniques, they can't be seen just as a cost. They've got to be seen as something that adds value to the reliability and the, improved efficient operation of that particular plant. And if you do have wins, whether it's an oil sample saves an asset or vibration spots something, abnormal in the operation, it's important to share those wins with the management, because the more wins, they may see from an operational standpoint or certainly from a financial standpoint, will help get that buy-in to see that it's not only a cost. There is cost benefit and significant or potential return on investments for spending the money on these condition monitoring techniques, but fundamentally saving money further down the line as well. And I think, you know, if you're operating or you're looking after multiple sites, trying to standardize what you're doing across all sites. So the way you perform activities, the way you take samples, so have those documented written processes that are available for everybody involved in the condition monitoring and reliability across all sites, has that visibility. So there's that consistency across all.
Thank you, Gwen. Adam or Dimitri, we've got a few minutes left if you want to contribute.
Yeah, I think speaking to a lab would be a good place to start, even if it's on initial things like getting a list of assets, finding out what the different lubricants are in them, what's there, having a chat about what your capacity is to take samples, how many people you have that you're able to, okay, we can maybe spare enough people to take 30 samples a month, or is it 30 samples a quarter, and then maybe discuss what are the key things to start sampling as soon as possible. And then as you see gains from this, roll the system out, and hopefully, as Danny has highlighted, if you have information and you're able to not do unnecessary maintenance, that frees up time to expand the program onto other assets, and then it's something, hopefully a virtuous cycle that keeps improving things and helps move things forward.
Absolutely. Adam?
Yeah, I would just add, not just management buy-in, you need everyone's buy-in for the program to succeed. So with a lot of applications, I was speaking to someone actually earlier this morning before this webinar, and they said, oh, I haven't got time to take all samples. And that is one of the fundamental things is well, you need to, the management team need to give the people the time to do the sample so they can then get the payback later on reduced time on spending on doing repairs and maintenance. And so that buy-in needs to come from every step of the chain, not just the management.
Just like to add, if I may, in support of what Adam was saying there was some research done in the States 10 years ago, I think it was, by companies who made that very similar point, that we haven't got the time and resource to do this extra work, which meant they couldn't move forward because they couldn't actually develop. And the research outcome was that if you spent just 1% of the resource that you've got eliminating defects on site, in 5 years' time you would have 30% fewer unplanned maintenance requests. So actually a small investment in optimization can pay big dividends in output.
Absolutely. And I know there's a stat that lubricants account for 2% of the maintenance budget, but they cause 40% of the maintenance spend on an annual basis. And Nicholas has just dropped a comment in, I know Dimitri touched on it, but that perhaps some lubricant rationalization to reduce inventory and possible oil cross-contamination. And lubricant rationalization is absolutely a massive part of a CBM strategy for failure avoidance. And as Dimitri said, the lab can support with that, where you may be unsure which lubricants have been used in which assets, or you just want a decent picture of how many lubricants are actually in use across various sites. The lab can absolutely support with that. And this person's trying to go to a CBM-based approach and struggling with lubrication practices that vary from site to site. And I suppose we need to remember that we use standards such as the 55 to guide us on how to start a CBM strategy, but it must always be optimized and moving. And your condition monitoring data, such as your oil and grease analysis from the lab, can help guide them lubrication practices, and where maybe on some sites they're not working quite right, or where maybe we need to change the practice. So we start with the guidance and the standards, and then we use the condition monitoring data and information that we're receiving to structure that in a way that specifically works for your site. I'd like to thank everybody for joining and viewing today, and for the engagement in the chat and the Q&A. It's been fantastic. Again, we will follow up with an email with everybody's contact details for people to reach out for support. The BINDT Lubrication Working Group are always happy to support. We take things in as a group on a really regular basis, where we can help people as a group. So you've got a really independent support from all of us. Just a quick reminder as well about the condition monitoring conference from the 9th to the 11th of June in York. If anybody's interested in attending that, you will see lots and lots of presentations similar to what you've seen today, but they will cover all aspects of condition monitoring, not just the oil analysis. So please reach out to the BINDT team if you're interested in attending that event in person. Again, thank you very much, everyone. We've finished dot on time, which is really good. Danny, have you got another word?
Just a last question. Is in front of you now are a number of members of the Lubricants Committee. You'll see there's a predominant lab presence, and that's fine. But if there's anybody on the call today who wants to come in as a user and give us their experience within the group, then I'd heartily invite them to make themselves available. Most of our meetings are online. They're not necessarily in person, and if they are, they're in the UK. But user perspective, I think, is critical here. And if anybody wants to share that, I'd invite you to join.
Absolutely. We're always open to having end users in the committee working groups to have an open session. Fantastic comment. Thank you, Danny. Have a really good day, everybody. Thank you so much for your support, panelists and presenters, and we'll see everybody very soon, hopefully.